strict permutations are really no more different than our factorial notation or our fundamental counting principle. So a permutation is simply an arrangement of things in a definite order. Again, something where order actually matters. The number of permutations can actually be calculated using this formula. Now, it's using the characters of NPR, which is actually the exact same way that you access your factorial. That's using your second and your PRB button. And the strict definition of permutation is just taking n factorial, so n different objects, after taking r the amount of time. So n factorial divided by n subtract r factorials. So if we look at the first example, that means that we'd have 7 objects, and we'd be taking just 2 at a time. Now, the first thing we'll talk about is just that putting it into factorial notation. So it'd just be 7 factorial over 7 subtract 2 factorial. Now we're just going to simplify it out. 7 factorial over 5 factorial, and then simplify further. 7 times 6 times 5. Oh, then our 5s are going to cancel off. Well, not just the 5, the entire 5 factorial. And 7 times 6 is 42. If you actually type that into your calculator, 7p2, you just type 7 first. Press your PRB, select your NPR, then type 2, and you'll get 42. Now, solving for stuff when we have unknowns, we're going to do the exact same thing. We just have n factorial over n subtract 2 factorial, and it equals 56. So we're going to simplify further. Remember, start with your higher number. N is higher than n subtract 2. So n, 1 less than n would be n minus 1, then n minus 2, and that's all that we have to go to. If you have more than 2 terms, you don't have to worry about simplifying or anything like that, because that's not the role of Foundations 30. Those would cancel off. Sorry, I should make sure it cancels off the factorial with it. That equals 56. N times n is n squared. N times 1 is negative n. That equals 56. So we would subtract off the 56 from both sides. N squared, subtract n, subtract 56. And then we would factor. Product of negative 56, sum of negative 1 would be 7 and negative 8. So this would be n plus 7 and n subtract 8. Won't go further down. Then we just say n plus 7 equals 0, n subtract 8 equals 0. So n would be negative 7, or n would be 8. And only one of them actually works. This negative, if you have a positive negative, it's really identifiable quick. You cannot take negative 7. So you can't have negative 7 objects and only take 2 of them. But you can have 8 objects and take 2 at a time. Type that into your calculator. You got 56. So our next example. How many 4-letter arrangements can be used using different letters from Steinerable? Well, we have 9 different objects. We're just going to use the quick shorthand, make our lives easier, and we're going to take 4 at a time. So just meaning that the phrase STEI is completely different than IETS. The order matters. And if we type that into our calculator, NP4, sorry, we get 3,024. And that's all there is to it. So other examples, how many arrangements of 6 or more letters, if we have use sign words or the word sign table, well, that means that we could be taking 6 at a time, 7 at a time, 8 at a time, or 9 at a time. Which one is the correct answer? Well, it's actually all of them, because we're talking about 6 or more. We're just going to have our answers and add them together. 9p6, 60,480, 7, 181,440, 8, 362,880, and 9p9 is also 3,000 or 362,880. You add everything together, plus 181,440 and 60,480, we get 967,680. And that's it. Now, just a little bit of a quick fun fact is that, long story short, 0 factorial equals 1. There's no other real reason for it, and you don't really need to know anything further than that. Okay. Next example, how many different orders might 15 runners finishing a 10K race? Make it easier. The distance makes no real relation. You could be talking about how many different orders can you finish running from the front of the classroom to the back of the classroom. So the distance doesn't really matter. But what is matter is that we'd have all 15 runners finishing the race, which just means that we have 15 objects or 15 people, and we want to order all 15. 15p15 is absolutely 1.3 times 10 to the power of 12. So let's say that'd be, let's say that's thousands, millions, billions, about 1.3 trillion. Because it does, if one person if Bobby finishes before Lacey, or Lacey finished before Bobby, that's completely different arrangement, and it's for every single type of arrangement there. All right, last example, how many different 3-digit numbers greater than 300 can be made using the digits 1, 2, 3, 4, 5, 6 if no digits are to be repeated? Well, we can do it 2 ways. We can do it the simple way, which is the fundamental counting principle. So we'd have 3 options. Again, remember, those are options. We have a total of 4, so we want to have it greater than 300, which means that the first digit cannot be a 1 or a 2. So this is a little bit grammatical. I'm just going to make a note to fix this one as well. So the first option, we only have 4 options. After that, one of these numbers, the 3, 4, 5, or 6, are going to be used. So if we use the number 6, so it would be 600 something, we would have 5 options left. And then, if no digits are being repeated, we'd have 4 left. And this comes out as 80. Where this ties into permutations is the idea that it's still going to use the same thing. We still only have 3 options. The first case has to have 4 options. But once we use a 6, we have a total of 5 options left and we'd have to choose 2 more numbers. So this entire last 2 options is 5 times 2, or sorry, 5p2. If you type that into your calculator, it also comes out as 80. Quick, fancy, we'll have some fun.